Here you go, Mr. Newton, hold this.
Oh, right, cheers there. What's on this week's note sheet then?
Oh, right, well, I'll talk you through it. What are these all examples of?
They're all variables.
What's a variable?
Oh, something that they can change?
Yeah, so something you could take on a specific value from a set of values, yeah. Okay. Now, if we're looking at something that's an experiment, the outcome of an experiment, I mean, could you think of an experiment, Mr. Newton?
Maybe. Oh, I've got it.
Yeah, yeah.
What's the dice?
Yeah, so rolling a dice, that would be an example of an experiment. So, if our variable is something to do with the outcome of an experiment, then it's called a random variable.
That makes sense.
Yeah.
Random variable.
Now, what different outcomes could we get?
Oh, we've got the numbers 1 to 6, so 1, 2, 3, 4, 5, 6.
So this, our random variable, could take on one of 6 possible values. It could be a 1, could be a 2, could be 3, could be 4, could be 5, could be 6. And writing them all down, that's what we call a sample space. That shows us all the different values that our random variable could take. Okay?
So that's just one random variable?
That's just one random variable, yeah. And in fact, let's call it x.
Oh, so x is like represents all of them?
Yeah, x represents all of them, and we might say little x, that's going to represent one of them.
Okay.
Right, but what do you notice about all these things?
They're discrete.
Yeah, they're discrete. They're particular values. It's not any value within a range, it's particular values within a range. And so in this chapter, we're just going to be looking at situations like this.
Discrete
Random
variables.
Exactly.
Okay.
Okay, cool. Is there anything else we need to know that we might have done to the video?
No, I don't think so. That's
Okay.
it.
All right.
Well, as long as someone doesn't try and use probability against this, I'm sure it'll be okay.
Yeah, I think we'll be fine.
Alright guys, just gonna go.
See you in a bit, guys.
Alright. I got a mega idea. Teachers here, they've not done the stats chapter 5. I reckon I can use this information to run a little money making scam. Armed with just this coin, PE will definitely be going. English probably. Maybe even Mr. Newton. They're having a laugh. Please not. I don't think so. Gonna go inside. See how PE feel about my game. Hey guys! Thanks, yeah, better luck next time. Totally wedged up. Oh yeah! PE do not know what they're doing. These guys will be going for a laugh. It's Newton. You'll play my Mr. Barker's amazing quadruple your money game.
Quadruple your money?
Well, what I'm saying, right? Got a coin. Flip it 3 times. You get 0 heads. Get 1 head, 2 heads, or 3 heads, alright? They're your options. 4 options, you get 3 heads, I'll quadruple your money. 1 in 4 chance, quadruple it if you get 3 heads.
What, for £1?
I mean, what are all adults here, right? £1. So
Yeah.
call it 10? £10?
10?
That's my usual minimum.
Nah.
Alright, for you, because I like you, meet you halfway. £5?
I think I've got a £5 note here. Let's go.
Beautiful. I'll take your £5.
Right, do I flip it or do you flip it?
This, you can flip it. It's a £20 note.
Where have you got all that money from? PE?
And English.
Oh.
Could be yours.
Right, what?
So, Flip number 1. Oh, it's not looking good for you. That's the tails.
Alright, how many heads do I need?
Out of 3,
Out of 3.
3. So you got 1
I got 1.
for pride.
1.
I mean, that didn't quite work out for you.
What do I win for that then?
So it's 3 heads for 20. I'm just gonna take this and go. It was 1 and 4, right?
Hang on. I'm going to check this. Okay, I want to have a closer look at Mr. Barker's money making game, and I'm going to try and represent it in a few different ways. The first way is a sample space, and this is just writing down all the different options in a systematic way. So in this case it's kind of a list. So let's have a look at the coin. 3 tosses of the coin, we get a tail, and head. Either, okay? We get a tail, and a head.
On the third toss of the coin, we've got a tail, a head, tail, head, and a head. You've got all the options of a tail first, okay? And then we can go for head first, and we'll just do the same with the options, tail, head, and
Head, tail, and head. Right, well, obviously I've realised now he's done me in, because there's only 1 chance out of 8 that I get 3 heads, okay? Damn that, Mr. Barker. Anyway, put that emotion to one side. Let's have a look at writing a probability distribution. This is the same thing, but we just write a slightly different way. So I want to have in the top bit here, I want to have number of heads. Now, I could have got 0 heads. I could have got 1 head. I could have got 2 heads, or I could have got 3 heads. And this is why I was trying to kind of calm me a bit, because he was saying there's 3 options, so 1 out of 4 chance. 4 options, so 1 out of 4 chance. But obviously we know this isn't actually the case. So let's have a look at these probabilities. Now we have to write it down in a special way. All these options are grouped as set, capital X, and we're going to pick individual values. So probability of picking out of the set of capital X, little x. So picking x equals 0 for little x. So 1, 2, 3. We can see 0 heads, there's only 1 chance of that. Picking 1 head, well, I think it's 3 chances. Out of the 8. And 2 heads, 3 out of the 8 again, and 3 heads out of the 8. I can tell this is right because all those probabilities look to 1. Okay, we'll have to use that fact later. Okay, so that's probability distribution. Okay, distributed across these values here. Okay. Exactly the same information, just presented differently. Okay. Probability function is another way of writing this. It's kind of getting the distribution and put it in a different way. So the probability x equals x, or from all the groups equaling little values of x, we've got 3 options. We've got this big curvy thing here, so we've got different options. Well, we either get an 8 for the probability, okay, and that was when x was 0 or 3 from here. If we're going to go for 3 8s, the other option it could be, that was when x equaled 1 or 2. Now there's no other options, but we could put the probability 0 otherwise. Okay. So the key thing you need to remember, this is called a sample space, where we're just listing all the options. This is called probability distribution in this table here. And this is called the probability function, which it takes the distribution, it's kind of write it a slightly different way. Okay.
Okay, so we saw in my clever money making game that this table for the probability distribution, now if we look at, say, this value here, this means that the probability that the value x from my set is 1, so 1 head, is equal to 3 eighths. Now similarly, I got here probability of 0 is 1/8, here the probability of 2 is 3 eighths, and the probability of getting 3 heads is 1/8. We've seen all this. But what that means is if we add them all together, I've got my 1/8 plus my 3 eighths plus my 3/8 plus my 1/8, well that equals 8/8 or 1. And that makes sense if you think about your probability chapter. The sum of all possible outcomes is going to add up to 1. Now we can use that information to work out some useful stuff. Now the way we write that notation is we could have the sum of the probabilities that x, big X, the set, equals little x, the individual values, or more commonly this is written as just the sum of the probabilities of x. They both mean the same things. Both of these notations mean we're adding up all the possible probabilities, and obviously if we're doing that, then the sum of the probabilities of x will always equal 1 in a discrete random variable. So this property is what we'll use in the following example. Alright, here it says we have a tetrahedral die, or dice, and it has the numbers 1, 2, 3 and 4 on its faces. So it's a 4-sided dice. The die is biased in such a way that the probability of the die landing on any number x is k over x, where k is a constant. Find the probability distribution for x, the number the die lands on after a single roll. So interpreting that, essentially what it's asking us to do is work out what this k is, this value k is, and using that to write out the probability distribution. Well, I can start by writing the probability distribution as we know it, with k inside it. So if I write x, and it's a 4-sided dice, so my possible values are 1, 2, 3 and 4. And the probability of x equaling x, well it says it's k over x. So when x is 1, that's k over 1, or just k. When x is 2, that's k over 2, k over 3 for when x is 3, and unsurprisingly k over 4 when x is 4. Now the way I'm going to work out what k is using that fact that we know that all of these probabilities add up to make 1. So I can write this as k plus k over 2 plus k over 3 plus k over 4 is equal to 1. Now if I factorise k, bring that outside and use a common denominator of 12, that would give me, well 1 equals 12 over 12, so that's 12 plus a half equals 6 over 12, so 12 plus 6. A third is equal to 4 over 12, so that's 4, and a quarter is equal to 3 over 12, so that's 3. And all of that's still equal to 1. And then when I add that up, 12 plus 6 plus 4 plus 3, well that's 10, 22, 25, so that's 25k over 12 is equal to 1, times by the denominator 12, divide by the numerator 25, and we end up with k is equal to 12 over 25. Good. So now I found out what k is. All I have to do to answer the question, find my probability distribution, is plug that value back into here. Just be careful when you're doing it. So I've got, if I do this in 2 steps for you so you can see, x and the probability of x equaling x. Well, for 1, that's just going to be k, so that's 12 over 25. For 2, probability that x equals 2 is k divided by 2, or a half times k. So a half times 12 over 25. Similarly for 3, that's a third times 12 over 25. And for 4, if we squeeze that in, that's a quarter times 12 over 25. And for my final answer, I'll just cancel down and simplify. So my probability distribution looks like this. I've got x going from 1 to 4. I've got the probability of any individual value of x. That's 12 over 25 for 1. This is going to cancel down to 6 over 25. For the probability of x equaling 3, that will simplify down to 4 over 25. And the probability of x equaling 4 will simplify down to 3 over 25. That is my probability distribution for this tetrahedral die.
We're going to look back at our previous example and try and apply these little inequalities to them. So if we're looking at probability of x is between 0 and 3, we can't include 0 and 3 because of these strict inequalities here. So it could be 1 or 2. Well, that probability is very easy. Between 1 and 2, we've got 3 to 8, 3 eighths, so that's 6 eighths. If you want to cancel that down, that's 3 quarters. Okay, nice and easy. For the next one, we've got between 1 and 3. We can't include 1, we can include 3, so it's going to be 2 and 3. So 3 eighths, 1 eighth, 4 eighths, we cancel that down, 1 half. Here, between 0 and 2, inclusive though, so we've got 0, 1 and 2. 0, 1, 2, so add them together, 1, 3, 7 eighths. I'll cancel that down. Should use my equal sign. And this one, just less than 2, which could be either 1 or 0, so 3 or 1, anything less than that, well, we haven't got any of that. So 4 out of 8, which is a half. There you go. So maybe if Mr. Barker had different conditions for winning his game, we'd have some different probabilities, and he could write them like that. Okay, so we're going to look back at the example we saw earlier about Mr. Barker's money making game, and we're going to look back at our probability distribution. And what I'm going to do, I'm going to draw a cumulative probability distribution. Okay, so I'm just going to add an extra column to my table. What cumulative means is it gives go up as we go. We can add up probabilities. So it's kind of using an inequality really. So you could use this function, use capital F of x when we're doing this. Okay, and what that means really is that the first one 0, fine, 1 8. The next one means probability of getting 1 or less than 1. Okay, so 1 or 0. Well, 3 eighths there, 1 eighth there, so 4 eighths. Okay, and then the next one, 2, it's probably getting 2, 1, 0, so 2 or less than 2. Okay, so that's another 3 eighths, so 7 eighths. A bit like cumulative frequency stuff that you do at GCSE. And then here, well, it's going to be 1, 8 eighths or 1. We know the total probabilities add up to 1, and that's adding up everything. Okay, so this f of x, capital F of x, represents this cumulative probability. I suppose we could write it down, capital F of x equals probability that x not is equal to x, but is less than or equal to x. Okay? Right, I think Dr. wants to go through a more detailed example with you.
Right, so let's have a look at this example. Now, first of all, we're asked to find the value of k. Now, the key to these questions, when we've got a cumulative distribution function, is to look at the last possible outcome, because we know when we've added up all the different possibilities, when we get to the end, it's going to equal 1. So the last possible outcome in this one is that x is 3. So let's look at f of 3. Well, we know that when we sub 3 into this, we get 3 plus k over 8, and we know because that's the last possible outcome, that must be equal to 1. So that is equal to 1. Well, we can rearrange this. So we've got 3 plus k is equal to 8, and therefore k is equal to 5. And so we know that this is actually equal to 5. Right, part B then says draw the distribution table for the cumulative distribution function. So it wants us to draw a table. So let's do that. And we put all our possibilities along the top. So x can be 1, it can be 2, it can be 3. And we're looking for the cumulative probabilities. Well, now that we know k is 5, this is just a case of subbing the numbers in. So if we want to know f of 2, then that is 2 plus 5 over 8, which is 7 over 8. If we're looking for when x is 1, do f of 1, which is 1 plus 5 over 8. Again, just because we know k is 5, just subbing the number in. And so that is 6 over 8, which is 3/4. Well, we already knew when x is 3, the whole thing, the cumulative probability is 1, because it always, at the last one will always be 1, because all the probabilities add up to 1. Right, part C then. It says, write down f of 2.6. Now, this is where we've got to remember we're looking at discrete random variables here. And so our discrete random variable x can only take the values 1, 2 or 3. So actually, if we're wanting to add up all the probabilities all the way up to 2.6, well, we'll be adding them all the way up to 2 and we wouldn't be adding anything extra after 2. And so actually, f of 2.6 is the same as f of 2. Because we wouldn't be adding anything extra on, because there aren't any values between 2 and 3. Well, f of 2 is just 7/8. Right, the last one, find the probability distribution of x. Well, again, this is wanting us to draw a table. But this time, we want the probability that our discrete random variable equals x, not the cumulative. Now, the key to this is to start right at the end. So we know that in going from probability that x is 2 or less to the probability of 3, we're increasing by 1/8. So that means the probability that x is 3 must be that 1/8, because it goes from 2 at 7/8 to 3 at 1 whole 1. The probability that x is 3 must be 1/8. Right, well, to work out the probability that x is 2, that's what we get when we go from x is 1 to x is being 2. So we need to look for the difference between these. Well, 3/4, that's the same as 6/8. So again, going from here to here, we're adding on 1/8. So the probability that x actually equals 2 must be 1/8. Right, well, what have we got left? Well, we know that these all have to add up to 1. So we must have 6/8 left, or 3/4. So that would be our probability distribution.
Business department, give them a miss. Get the coin ready. These yuppie types, they won't know what's hit them. Rich pickings in here. I thought PE was good. Rumour has it, this could be a gold mine. God damn it, they've gone home. These arrogant scientists, they'd have definitely gone for it. If science have gone, no way they're still here. Now to lay the honey trap. Rumour has it, she's got money to burn.
So, Mr. B, have you got many takers on your scam?
Whoa. I object to scam, but in my legitimate game, I'll tell you what, it was tough in science, most of them have gone home, but English, PE, history.
Oh wait,
Just
Dawson's here.
Just
We can get
bamboozle them
Dawson.
with a bit of numbers.
Do Dawson.
Fancy your chances, sir?
No.
He's head of department for a
No.
reason.
I'll lose money. I'm not going to be conned.
Con?
Mr. Barker, you haven't been conning teachers out of money, have you?
They're all over the age of 18.
How's the game going, Mr. Barker? Any takers?
I'll tell you what. Nothing to rival PE, but I'm hopeful.
God, those steps are awkward.